All right, let's get started. So last time we started introducing these kind of more physics-based methods on our way to introducing simulated annealing. Let me get rid of that mouse on the screen here. And so the quick overview of that is that when we think of physical systems, they have kind of a natural optimization-like picture that emerges, kind of similar to how we think about evolutionary systems. That picture being that a physical system can be in the various components, the various high-dimensional components of a physical system, like this tablet, the screen behind me, that chair, myself, made up a lot of tiny little components that are moving around, high dimensional representation. So we call those things microstates, and we can think of each one of those microstates or configurations, and these are basically like the genotypes in our previous GA. So these are high dimensional. And we know that those microstates exist or can be evaluated within an energetic landscape. So there's energy. And so some microstates have more energy than others, the same way a ball being held at height has more gravitational potential than a ball that's close to the ground. So we could imagine that each configuration of these things might be hopping from one state to another, sometimes hopping up the energetic landscape, sometimes down below. So if we were to plot this energetic landscape over this high dimensional space that I've compressed down for simplicity into one dimension here, as if I could sort of order these microstates, where this is like microstate 1, this is microstate 2, and so on. If I sort of enumerated all of the microstates, then we would get, a possible landscape that might look something like this, where nature will tend to bring things to this minimum energy configuration, which you can think of often as the sort of purest configuration. So it typically is going to have the fewest imperfections, going to be the smoothest, and so on. But there might be these traps along the way. So there's maybe some dislocations or irregularities. And so in order for it to for a system to make it from this point to this point, it needs to have enough energy to make it over this this little potential well. It needs to get out of this potential well. So it needs enough kinetic energy available for it to pop out of the potential well. And so we know that the energy available, the kinetic energy available to these microstates is proportional to the temperature of the object. And so there is this, so we can think about this as kinetic energy available. I'll say average kinetic energy is going to be proportional to temperature. And in physics, they specifically say that the average energy is equal to kT, where this K is this constant proportionality called Boltzmann's constant. And so the basic idea here is that if you have you could say if KT is greater than this height, then barrier is surmounted. Otherwise, you might stay in that barrier. So in other words, if the average energy available to the microstates is greater than this height, then you will tend to be able to go over this and find your way into adjacent valleys of this energetic landscape. But if T is very low, So if the temperature is very low, then there's not enough energy available and you get stuck inside here, just bouncing around inside this one. So you get trapped into a local minimum. And so in real physical systems, the annealing process it sort of heats up object. You know, you can imagine this sort of melting it or recrystallizing, you know, up to recrystallization, and then slowly cools object so that it hopefully will end up landing lower energy configuration. And so this is a common method to sort of purify materials, is if they have a bunch of imperfections in their structure, you can melt them and then cool them slowly, and hopefully you'll catch them in a low energy configuration as opposed to catching them in one of these points up here. And so this annealing process, the thought is that if we can manage to take a design problem that's a very high dimensional design problem, if we can move through the design space in a way that simulates how physical systems move through the microstate configurations, then maybe we can also do an annealing process where we can start out in a random configuration and then heat our virtual configuration up, allowing it to explore a bunch of alternative configurations. And as it's exploring, it's finding configurations, some that are better than others in terms of our optimization objective, lower than others. And then if we cool it, they'll get stuck in those new spots, hopefully, you know, down here in an optimization objective. And then we'll end up finding that global optimum here. So, so we need to sort of find a way to implement our optimization objective as simulated energy and simulate. And that is the simulated annealing metaheuristic. And this is for minimization, but you can, of course, change a maximization problem, minimization. Ooh. You can change a max problem into a min problem just with a negative sign. All right, so so that is, you know, that's kind of where we're going. And so last time, you know, we started to say, well, how do you simulate what physical systems do? And I focused on this concept of entropy. And so we know that physical systems, statistically speaking, tend to move from lower entropy to higher entropy. And I talked about how entropy sort of is, from last time, entropy is a measure of the amount of, say it's a measure of the remaining degrees of freedom or uncertainty left in a, I'll say in a macro state, and I'm referring to the remaining degrees of freedom, I'll say in a macro states, micro states, how about that? Or distribution. So this is a measure of a distribution. So we aren't going to have to, I'm not going to force you to calculate entropy in this class, but I want you to know that it can be calculated because there are going to be certain critical distributions that come from the entropy maximization process that you've likely seen before in a lot of your classes, but no one's ever told you that the reason you use those is because they're maximum entropy distributions. So, this can be written entropy as proportional to, if we have discrete microstates, this can be viewed as the sum of the probability of the microstate times the log, I'll do log base 2 of the probability of the microstate, which is just the expected value for a probability distribution, a probability mass function of the log base 2 of all the probabilities of the states. Or I should say, put a negative out here, which also can be written as the expected value and so on. So for those of you who've taken any courses in information theory or are familiar with information theory, then this might look familiar to you because it has to do with how many bits are needed on average to represent a piece of a configuration. Like if I wanted to represent the position of particles in this room, if these particles could be everywhere in the room, then it might take me a lot more bits to be able to actually pin down where every particle was. But if these particles could only be in one place in the room, then on average, I might not need that much information. And so if most of the particles are in the one spot that's over there, then all I really need to do is first confirm it's in that one spot. If I give you a 1 that tells you, okay, it's over there, I'm done. If instead it's somewhere else, then I might give you a 0, and then I follow it with an encoding of where it is in the rest of the room. So on average, I actually don't need that many bits because most of the particles are stuck in that corner because I've compressed them into that corner. So most of the time I just send you a 1 to say, yes, they're up in that corner. Only some of the times I send you a 0 followed by a huge string of bits to tell you where the particles are elsewhere. So we would refer to that as sort of a low entropy configuration because I don't need to communicate much to tell you where the particles are because I know they're all going to be up in that corner most of the time. A higher entropy configuration is one in which I always have to send you every single position. So I don't know where it could be. I don't know ahead of time. It could be here, it could be there, it could be over there. And so I have to send you all of those coordinates every time. So with high probability, I'm going to need to send you the entire map of the room every single time you ask me where the particle is. And so that is a higher entropy configuration, requires more bits for me to communicate where things are. So that's kind of the connection to information theory there. There's sort of a one-on-one mapping there. And this is for discrete microstates, what I wrote up here, but this also works for continuous. And so this is our discrete case. And it also works for the continuous case where this entropy is going to be proportional to the integral of the probability density function at the state times the natural log of the probability density function integrated over all of the states. So yeah, all of the states. And so I can, this also can be represented as an expected value. And you can also think of it, and this is also a negative, the positive version, something along these lines. So there are ways for any probability distribution out there, normal distribution, uniform distribution, any of those, I can calculate the entropy of those distributions, discrete, continuous, whatever. I can tell you how many bits on average are needed to communicate things that are drawn from that distribution. That's one way to view this. The other way to view it is, again, is the remaining uncertainty after I've kind of given you that distribution. So if I tell you that, that there's a wear pattern in the carpet because most of the time people, come into the seats, but then the instructors always walk a certain path. And if I were to pull up these carpet squares, if there's a carpet pad underneath these carpet squares, I don't think there are in this case, but let's pretend, then the carpet pad underneath there might have a wear pattern underneath it. And that wear pattern, due to the central limit theorem, is going to tend to be normally distributed. So it'll be a high wear right here, and it'll be a low wear out here. And so I can communicate to you that there is a normally distributed wear across here, and I can calculate the entropy of that normal distribution. And what that that's capturing is that I'm effectively telling you most of the wear is here. There's no wear over there because nobody walks on that rubber strip that separates the carpet from you guys. And so there's absolutely no way that we're going to find any wear there, but there is some uncertainty left over here. So sometimes people walk over here, sometimes people walk over here. So there's a little bit of uncertainty left over here. So the normal distribution is not, for this room, the highest entropy distribution. The highest entropy distribution would be a uniform wear pattern where I have no idea where people walk because it's uniformly distributed over this whole thing. But the normal distribution is a slightly lower entropy distribution because it concentrates things where my uncertainty is really just here. If there was always a robot that followed a line, like it, followed one of these lines in between these carpet squares, and that's how, so like it was a telepresence TED. So I would be at home and a robot would come in and it would be rolling back and forth on sort of a virtual track. Then if that robot was always on that same track, there would never be anywhere but assigned this one line. And that would be the kind of lowest entropy distribution because the cross section would be deterministic. So in that case, there'd be no bits left over. So it's the lowest there. So it's the highest order distribution. So high order kind of means deterministic, no uncertainty left over. High entropy means low order, tons of uncertainty left over. That's our definition. Yeah.
So could you say that entropy is somehow related to standard deviation?
You could say entropy is related to standard deviation. Standard deviation is a parameter we use typically to characterize what we refer to as location scale distributions. So when you can characterize a distribution with a standard deviation, then typically the ones that will have wider deviations will be ones that'll be higher entropy distributions. Yeah. All right, so that's the basic idea of entropy. So any questions about this basic idea of characterizing probability distributions by how much uncertainty are in them, where some distributions are somehow going to have more uncertainty in them than others? This is also sort of frustrating when so a lot of people use the term random and non-random, but what they really mean is uniform and non-uniform. So there's a lot of times that that someone would say, oh, they didn't draw something randomly, they drew it from so there's somehow a difference between if I was going to call on you for questions and I decide, I could call on you all uniformly. So there's so many of you in the class, I can call on you with 1 over that number probability, or I could always pick on 2 or 3 of you. And among those 2 or 3, I wouldn't call in only one person. They would kind of go back and forth. And so some people would say that if I was calling people randomly, I'd call on everybody with uniform. But if I'm not calling on them randomly, I'm only picking on 2 or 3 people. To me, those are both random, but the picking on 2 or 3 people is non-uniform. And by that, I mean it has lower entropy. So typically when people order things in their head, they want to order things by it's more random or less random, but they just don't have the language for it. This is the language for it. Whenever you wanted to say something is more random or less random, what you mean is it has higher entropy or lower entropy. So that's how we more technically say that. Okay, I see a question online. Was it that high ordered equals low entropy and vice versa? And someone confirms that, yeah, high order is low entropy. And I'm happy to write that down if that's helpful. So high order, e.g. deterministic, equals low entropy. Now, I mentioned that physicists came up with this idea in part to try to understand where the heck we get the notion of time, the arrow of time. And the thought is that the universe started in a high order configuration where all of the universe was compressed to a single point. And when the universe started in that high order configuration, entropy 0, low entropy configuration, it had nowhere to go but to get more and more disordered over time. So the thought is, the reason we have an arrow of time is that we are constantly unrolling the high order at the start of the universe. And so we're gradually, the universe as a closed system has the property that delta S is greater than 0. So there is a tendency toward higher entropy. And that's going to be important for us in this just a slide here. But so the way that kind of links, so the physical spaces here is, you'd say, well, then why the heck is there this tendency toward, or why the heck there's this apparent asymmetry? Like the laws of physics can really go backwards and forwards. If you replay a videotape forwards and backwards, you can actually come up with a physical narrative, how it's physically possible for that videotape to be played backwards. And all the laws of physics still work. But then, so why is it so clear when the videotape's been played forwards or backwards? And the thought is that because the universe started in this high order configuration, it set up a gradient that we've been riding for billions of years coming on down from that. So we've started out effectively with everything in one point, and now things are spreading out. Some particles are moving, some particles are slowing down, and you're getting more and more diversity over time. Until eventually heat death, when you reach the maximum entropy configuration of the universe, at that point, no information is at the lowest energy. You have a lot of information, all the universe is at a point. In the highest entropy configuration of the universe, all matter is, there's sort of there's no difference between things now and things later. And so you lose all of that information. It's sort of an irreversible process. You're just stuck in nothingness and no information. So highest uncertainty. So we're gradually moving from high certainty to low certainty. That's what this second law of thermodynamics is right here. So this is the second law of thermo. And if you take courses on thermodynamics of computation, et cetera, then what you will end up learning is that what a computer is doing is it's managing this. So every time your dynamic RAM inside your computer, it wants to constantly lose that memory. And so it constantly has to be refreshed. And so you're constantly dumping energy into your computer to maintain that dynamic, that RAM, to keep it from decaying away. And in doing so, your computer is getting hotter, and it's pushing that heat out into the outside environment, and it's actually creating more disorder. So as you create more order inside a system, you necessarily create more disorder outside a system. And so you make things, to keep things more deterministic inside the box, you are going to make things more non-deterministic outside the box. And so you're constantly going to make things more and more random. So life and computation's ability to keep itself ordered actually hastens the movement toward the heat death of the universe. And so people, people claim that, one of the functions of life and computation is to actually accelerate the rise of entropy in the universe, because as we maintain our bodies, as we maintain this building, et cetera, we're actually increasing the net amount of entropy to the world, to the solar system, to the universe, far more than we would if we weren't here. So even as we maintain order, we actually create even more disorder than we would if we weren't maintaining order. So anyways, that's the kind of philosophical side of this. So entropy, really important for thinking about time and so on. So how do we make use of it as engineers? And so there's the statistical interpretation of entropy being the maximum disordered configuration. That means that we can actually interpret it as the so-called the maximum entropy distribution is the distro with the, I'm going to say, least bias for given constraints. Now, what do I mean by that? So what we can do with the math that I showed you there, and I'm not going to go through all the details, it takes a little bit of calculus of variations, but in principle, you can do this. You can say, take some constraints. So imagine I have the constraints like, I'm considering positions of particles in a box. And so I would like to maybe simulate the positions of particles in a box. And I'd say, well, so for the position of particles in a box, all I know is that there's a constraint where there is, if I only consider the horizontal position, you can do this for all 3 dimensions, but let's just say I'm worried about particles in the horizontal dimension, then I know there is a lower bound on where they can be, and there is an upper bound on where they can be. So that's the lower bound, upper bound, and this is our position. So ahead of time, that defines the box. Somebody says, here's a box, I want you to simulate particles in the box. Like, just put them somewhere in the box. And you have to say, well, where do I put them in the box? So as a programmer or a designer, an engineer or whatever, then you could put them anywhere, right? You could decide, I'm going to put all the particles clustered against the left side. So they could be all clustered by here. They could be here. They could be I could take whatever the distance here is and divide by 6 and put them on little posts every 6th of the box. I have total freedom to do that. But my choice may reflect something about me. In other words, if I'm not careful, how I choose where to put those particles in that box is going to be a reflection not of the fundamental constraints, but of some bias in my head. So I maybe don't want to, or another way to view it, maybe I'm not simulating particles in a box, maybe I'm trying to tell a robot where to go search. So I'm telling it, here's a box, you need to figure out where to go search, go find a position and go search. And I can say, well, what position should I have the robot go to? And I can say, well, I could have it start at the left side. I could choose distributions of robots throughout the box. My choice of that distribution may reflect more about my personal biases about where I like robots to be in the box than anything else. And somebody else comes in there and they might have their own biases and so on and so forth. So I would like to come up with a distribution that respects these constraints, but does not add any other more information. And so that is the MaxEnt distribution. So I can solve for this. I can say, what is the, how I can maximize those entropy formulas that I just wrote on the previous slide, subject to these constraints. So it takes a little bit of calculus of variations, some Lagrange multipliers, but it's possible to do. And when you do it, then the MaxEnt distribution over all distributions subject to that constraint. So we're maximizing entropy subject to that constraint. So I'll just refer to it, subject to is equal to, does anybody have a guess what the maximum entropy distribution is for the constraint of a lower bound and an upper bound, and you know nothing else about the system? What is the uniform distribution? Right, so that's the uniform distribution. Let me see if online, I think somebody else also guessed uniform. That's right. So the MaxEnt distribution is the uniform distribution, uniformly distributed between L and U. So that tells me that I should make my X distributed as the uniform distribution. So that's one of the reasons why we choose the uniform distribution, is that it doesn't add any other. I could have chosen the triangular distribution. I could have chosen a beta distribution with all sorts of interesting parameters and make it kind of, bias the density, but there's no reason for me to bias the density. I should have it sort of symmetric chance of hitting anywhere along here. So that's where I get the uniform distribution. So that's maybe an easy one. So let's consider a little bit more difficult one, a more interesting one. So let's consider so as kind of another related example then, what about the space between particles in a box? So, or a line, just to be simpler. So the idea here is that the constraint is that if I have, I think, n+1 particles maybe, then I'll have n distances between them. And those n distances have to add up to the total length of a line. And I know that each one of those distances has to be greater than or equal to 0 because they're distances. So this tells me that the average distance between particles is 1 over n times this sum of distances, which is just going to give me L divided by n. So that's really my constraint. So my constraint here is that the average distance is equal to L divided by n. And I also know that each distance, because it's a distance, is greater than or equal to 0. So those are my two constraints for this problem. So, so someone tells me, I want you to drop points on a landscape. And all I want is that the average distance between those points should be some fixed value, in this case, L over n, whatever. And those distances, because they're distances, all have to be greater than or equal to 0. So you're going to need to give me a distribution that gives me only positive values and has a fixed average. There are a bunch of distributions you could come up with that way. You could come up with a uniform distribution from 0 to 2L over n. And if you did that, that would give you an average distance of L over n, and all the distances would be greater than 0. But if you did that, you would be preventing there from being any distances outside of 2L over n. So just choosing the uniform distribution would not be a good choice here, because it adds in your own personal biases as an engineer and so on. So instead, I can solve using this constraint, here. I can then solve the MaxEnt. So that's my constraint. And then I go and I solve the MaxEnt problem. And the MaxEnt distribution that satisfies this is going to have these distances distributed as an exponential with average L over n. So as a reminder, the probability density function for an exponential is just that right there. So, so that here is just an exponential. So this is one of the reasons we see exponentials pop up more and more and more, or not more and more, but all over the time. Whenever we're thinking of models, we often say, well, we're going to assume it's exponentially distributed. And we often think that we're using exponentials because they're mathematically convenient, because they are mathematically convenient. They have lots of nice features and properties. But the biggest reason we started using an exponential is that very often people give us data that look like this. They say, I know the average. I know the data points are all positive. That's all that I've captured about it. And so the least unbiased choice we can make without them giving us any other information is that their data are exponentially distributed. That allows us to have, in theory, rare but very, very giant data points. It also allows us to have small data points and so on. For this box case, it's a little bit contrived because there is a maximum distance between particles, the length of the box. So in reality, I could resolve this problem where I had that upper constraint. But if you consider it to be a very, very large box, then that distribution is going to be similar to this one here. So that's the MaxEnt distribution when all you know is the average and that they're positive. Now, what's interesting perhaps about this is if you were to draw particles, so going back to the previous thing with uniform distribution, if I were to draw particles uniformly in position in a box, maybe it wouldn't be surprising to know that after you've done that experiment, you could do that. You go into MATLAB or Python or whatever and create a virtual box and draw 100 particles at positions that are just drawn from the uniform distribution, from the lower bound to the upper bound, and put them in that box. Sort them so that you know that like the ones from left to right, and then measure the distances between them. And what you'll find is the distances between those particles will be exponentially distributed. So it may kind of make sense that the MaxEnt position distribution, the maximum entropy position distribution, happens to also give you the maximum entropy delta, distance between those positions in distribution. Or if I were to say it the other way, if I were to take these distances and add them up, starting from the left and going all the way to the right, and putting particles at each one of those distances, I would get a uniform distribution of particles throughout that box. So there is a relationship between the uniform distribution and the exponential distribution. And this also works in time. So if I wanted to, this is kind of the more common case you might see in modeling. And if you've ever taken courses in queuing theory, et cetera, then this should be somewhat familiar, is that you could say, well, what is the time between arrivals with given an average, or given say an average arrival rate, or equivalently, an average inter-arrival time, sort of equivalently. And then so there, my constraint is that the expected inter-arrival time, or inter-arrival interval, is mu, or the rate is 1 over mu. So maybe I'll just make that t to make it easier here. So I'll say the expected time is mu. I know that t is greater than or equal to 0. And so not surprisingly, the MaxEnt distribution is the one where t is distributed like an exponential with rate mu, or f of t is equal to mu e to the minus t over mu. Yeah. So the reason why when people say, on average, people arrive to the bank at this amount of time, if they don't give you any other information, the reason you choose the exponential, one of the reasons you choose the exponential, there are other mathematically convenient reasons, and we can sort of argue that there's some other, possible ab initio from first principles reasons, but really they all go down to this. The reason we choose the exponential is it's the least unbiased way we can model individuals where all we know is their arrival rate. So if we chose any other way, even if it matched in the average arrival rate, we'd be inventing other characteristics of that distribution. So the MaxEnt is the kind of most honest way for us to come up with a distribution that has the desired expected arrival rate or expected time in between intervals. And that is, so this hopefully, to some of you looks familiar, because this is exactly the assumption of a Poisson process. So in a Poisson process, the interarrivals are come from an exponential distribution. So a Poisson process represents the least biased model of encounters with known arrival rate. Okay. All right, so as you're thinking about that, any guesses to, so what about, say when I know somebody tells me I have a known mean and known variance. And so if somebody tells me that I have a data set with this mean and this variance, and that's all they tell me. They don't give me a histogram or anything like that. And so I need to choose a distribution for this. So any guesses as to what the MaxEnt distribution under these constraints would be? With a known mean, a known variance. I see a bunch of guesses online, which are coming up. And let me see if there's any guesses in class. Known mean, known variance, that's all you know. It could be a negative value, it could be a positive value. Gaussian distribution, so I see a lot of normal distributions. Gaussian distribution, another name for normal, and that's what I'm looking for here. So if you were to solve the maximum entropy problem with that constraint, then you end up getting that X is going to be normally distributed with mean mu and variance sigma. So there are central limit reasons why we often use the normal distribution, but there are also entropy-based reasons that we use the normal distribution. The normal distribution is the least unbiased way to model data when your data has only been given to you with a mean and a variance. That's the most honest way to deal with that. Now, if somebody then gives you a histogram and you see that it doesn't look bell-shaped at all, well, that's more information that now you can impose on your model. But if the only information you've been given is that it has a given mean and a given variance, then all you're really left with is to use a normal model for that. So yeah, that's, and so there's a comment online. Are these constraints on the position of a particle box analogous to the positions of electrons in orbitals? And I don't want to drill too far down into that, but I do want to sort of back up a little bit and answer that in some ways, yes. In other words, the way physicists think of distributions is they think about the amount of uncertainty left, and they assume that nature is, unless there are constraints that they haven't modeled, they assume that nature is going to sort of have symmetry across uncertainty. In other words, that's one of the reasons that it kind of reaches max entropy. So it is the case that when you model a physical system, once you know all of its constraints, if you don't have any other information about it, that's part of the way where physicists get their distributions, is they assume that it's maximum entropy across that. There's a guy named Jaynes, I think Jaynes, I think. So check spelling, but I think I've actually got articles on Canvas in this unit from Jaynes, who established this or formalized this idea that distributions in physics reflect this idea that physical systems are going to put their particles in ways that are kind of maximally uncertain relative to the constraints. And so if you absolutely know that there's a floor and there's a ceiling and there's walls, then you know that particles are only going to be inside the box, and they're not going to be clustered up against the wall. They're going to be uniformly spread over the whole position. If I open that door, then after a transient period, they'll be spread through the whole building. And that's the maximum configuration for these constraints. And so that does permeate physics. So it is a part of that. All right, and then so the last example I want to give that may seem more relevant, perhaps, is MaxEnt applied to natural language processing. And this is where actually MaxEnt kind of got its start in informatics, in thinking about NLP in computer science, but it's now found its way into a bunch of other fields for similar reasons. But the basic idea was, and I'll just motivate this with an example. Imagine that you have after someone types a word, then you have a 40% chance that the next letter will be an A or an AN. And I don't know which one it's going to be because I don't know what word comes after it. And I know the reason you choose A or an AN has to do with the next word that follows it. And so I have this constraint now that the probability of an A plus the probability of an AN is equal to 40%. So that becomes a constraint on my system. And then I might say, well, but other articles might be possible. So I might have a 20% chance of the being the next word. So I add another constraint where the probability of the is 20%. Let me see if I added any others. Okay, yeah, that's it. So those are constraints that I know that are coming up here. And then I guess then that any other word will be what's left over. So those are the constraints. So the question is what is the right distribution? So what distro best models the next word? And you could come up with a lot of distributions that these constraints hold, where the probability of this word is 20%, and of these two words add to 40%. You could come up with a lot of distros for that. Well, what the CS community did is they said, well, with this particular example, we are going to answer this by solving the MaxEnt problem. So I choose the MaxEnt distro, and that gives me, over all words, it will give me the maximum entropy distribution that satisfies these constraints. And by doing so, this will be the distribution that reflects the least bias in the developer. So it's a purely sort of automated way to remove bias from the choice so that the resulting choice will be a distribution where that if I draw randomly from it, I 40% of the time will get an A or an AN, and 20% of the time I'll get a the, and the other 40% of the time I'll get something else. But I don't have to think about what's the best way to spread the rest of that 40% over the rest of the words. I don't have to think about the best way to spread this 40% over these two words, and so on and so forth. So the MaxEnt does that for me. And as expected, you might expect, well, this 40% is probably going to get spread equally over these two words. The other 40% might be spread over all of the other words, out here equally. And these are the only ones that will kind of be held up. I haven't done this particular problem to see what the MaxEnt is, but I expect that will be what it is. But you can imagine getting into much more complex examples where I look at a corpus and I can say, looking over the entire corpus of this language, then I know that there are certain regularities where after a certain word, other words follow. And I can then take those regularities, embed them as constraints, and then run a MaxEnt, and then generate a distribution of what word will come next. And that distribution, maybe if I rank by probabilities or whatever, will end up being the suggestion list that Google pops up when it's trying to autocomplete what you're typing. So that's an example where you can use these MaxEnt methods to do these sort of human-computer interaction sort of things. Okay. So let me see if, like I mentioned, there are now people use this not only across NLP, but there are some MaxEnt methods are used across a wide range of other fields, anthropology, so anthropology, archaeology, ecology. And so how are these used? So typically in these types of cases, what people will do is they'll look at where artifacts or species have been found, and then they'll ask, where's the best place we should look next, given the constraints we know? So you look down the map, you know, there's rivers, there's trees, there's mountains or whatever, that gives you spatial constraints. And then you look over where things have already been found, and those can also give you constraints on things. So then you can ask, where is the least biased next place to look based on all of the information that I know about the system? And so that's a little bit like saying, once I've put up my walls, like I've put a mountain here, I've put a river there, and so on, and I already know that some of the things have been found here, then I can kind of ask, if this were particles in a gas, then where else would I imagine particles would be clumping up in the room? And then I'm going to go to that part of the room and look for those particles. And this has been very successful to guide searches for things. And so there are MaxEnt methods in robotics as well, where you can sort of figure out, like, based on what I know so far, where's my next best guess of where I should prioritize my search? And you can look up that. So these are have been around for ages. So if you're interested in this sort of idea of how do I come up with a good search direction based on the constraints I know from stuff in the past, then you can look up this MaxEnt, and it's usually written that way, capital M, capital E. All right, so that's something that I wanted to, it'll be important for simulated annealing here. So we'd like to get back to that, but I needed to kind of cover that first. So any questions about this MaxEnt stuff? Line I see here, still talking about the normal distribution, and then down at the bottom, okay, nothing new. Makes some sense. Okay, so getting back to the physical simulation process, then we want to, there is a MaxEnt problem here. And that is, I know that I want my system to be moving around at thermal equilibrium. And I have already said that at thermal equilibrium, that my average kinetic energy is going to be equal to KT. So it's going to be proportional, or in other words, the average energy is proportional to temperature with this constant in proportionality K. This is a constraint. So with this, I can then ask, what would the distribution of energy be across microstates given this constraint, given that all of the energies have to be greater than or equal to 0, and that the average energy is equal to KT. So these here are constraints on distro of energy across microstates. Okay, so and so what this allows me to do is it allows me to come up with a motion, an ability to say, when I'm at a particular microstate, how likely is it that I'm going to move to another microstate? Because I will know that at thermal equilibrium, I can sort of ask, how likely is it that I'm going to have enough energy to jump from one level to another? And so the MaxEnt solution to this, we've already seen it. So the MaxEnt distro is going to be, I'll say, the probability of being in a state I is going to be equal to the and so I'll just write this out and then we'll talk about it. Okay, so basically, this here is sort of a discrete sample of the exponential distribution. So we know from before that given these constraints, then I know that that if I consider across a continuum of microstates, that continuum is going to have an average energy of kT, and all of the energy is going to be greater than or equal to 0, then I know this is going to give me as a max entropy distribution, the exponential distribution. So it's going to be an exponential distribution of energy. So there will occasionally be there will occasionally be bouts of kinetic energy that will be very large, but most of the kinetic energy will be down here around kT, and a whole lot of it will be less than kT. So these are sort of the energetic jumps available to the microstates, describing how much money sort of is in their energetic bank. And so, so this here is kind of telling me that given a microstate I, then I can sort of say that that if I know the energy of that microstate, the probability that that state will be in that microstate will be this exponential distribution, where down here, this is just normalizing across all of the states. So this down here is often written as Z, and it's called the partition function. And really all this is saying here, because this is just a normalization, is that the probability of being in any particular state is proportional to the exponential of the energy of that state divided by kT. So what I'm trying to say here is that if kT is the average amount of energy available, and EI is the energy of that state, then you can compare EI to KT, and that will kind of tell you whether if EI is much greater than KT, then this number is going to be very low. If EI is much less than KT, then this number is going to be very high. So this allows you to turn energies into probabilities of making these jumps. So I've written this as energy, but you can also think of it as jumps in energy. And that's what we're going to see here as we start building the simulated annealing algorithm. And so the idea being here is that this is giving me a likelihood of being able to make certain jumps based on how they compare to KT, with large jumps, with jumps requiring energy larger than KT being very unlikely, jumps being very lower than KT being less likely. So this should, for those of you in machine learning, this should maybe look familiar, as this basically is the same idea that you see in softmax, which is a method when you're building multi-label classifiers. You have particularly, you want to say, is this a bird? Is this a cat? Is this a dog? Is it whatever? So I have multiple labels, and I can assign probabilities to those labels. And then export a distribution across all of those labels. And very often you take information from inside your statistical inference engine, your neural network, and you normalize them so that you end up having an output which where all the probabilities add up to 1, and you use the softmax function, which looks a lot like this. And this is where they got softmax. And what this distribution actually is called the Boltzmann distribution. And all the Boltzmann distribution is just an exponential distribution. It's a distribution across high dimensional microstates that produces an exponential distribution in the energies of those microstates. That's what I'm trying to connect here back to this MaxEnt idea. So where I'm going with this is that, let's say I want to say, well, if I want to move, if I want to consider a movement from state I to state j, well, what I can do is consider the likelihood ratio and let me just verify I put in my example j as the new state. Is just going to be the ratio of those two numerators, because the denominators all cancel because it's just normalizing across all the states. So that's going to be e to the, well, it's basically this whole thing is just going to end up being e to the negative delta ji divided by kt, where this delta ji is just equal to ej minus ei. And so this is kind of what I was trying to get to here, is that if I know that I have a certain energetic state at some microstate j and some other energetic state at microstate I, if I'm currently in state I, then delta ji represents kind of the energetic jump that I need to get from one microstate to another. And this likelihood ratio provides me kind of a mapping that tells it how likely is it for me to make that jump. And if my delta ji is far greater than kt, then it is likely jump or unlikely jump. And if delta ji is less than kt, or approximately 0, then this is a likely jump. So again, we think of kt as kind of our energy budget, and we think of delta ji as the cost of a jump. All right, and so this ends up becoming important to the first class of what so this ends up becoming the main driver for the first set algorithm that was developed to simulate microstate evolution at thermal equilibrium. It's all based on starting at one microstate, choosing another microstate at random, querying whether that randomly chosen microstate has a favorable likelihood ratio or an unfavorable likelihood ratio, and then jumping to them based on that likelihood ratio. And that tends to generate at equilibrium microstates which abide by the Boltzmann distribution. In other words, it finds microstate distributions that end up having exponentially distributed energy landscapes, or exponentially distributed energies for a given temperature. So, this is our kind of connection to MaxEnt, and I want us to keep this in mind as we then now talk about the Metropolis algorithm, which then makes use of this. All right, so I know that was maybe not the clearest path through this, but I think things will get clearer as we go into the Metropolis algorithm. But are there any burning questions that I can maybe try to answer, even though I'm feeling a bit rusty today about this? So the likelihood represents what are our chances from going to state I to state j. That is a fine way to view this likelihood ratio, is the whether starting in state I, evaluating some other random state, and whether it seems like this is a jump that possibly could be made given the temperature in the system. So if the temperature is very low, all jumps will end up becoming outlawed. If the temperature is very high, then you can basically make all jumps for free. Okay. All right, so where does this come up and why is this this relevant? So if we cut to some computing history. So back in 1953, there was a researcher named Nicholas Metropolis. How many of you have heard of the Metropolis algorithm? Anybody? How many people have heard of MCMC, or Markov chain Monte Carlo? A little bit more, okay. So the Metropolis algorithm was the first MCMC. It's sort of where all the other MCMCs kind of were derived from. So Nicholas Metropolis and others and this was back in 1953, this was an interesting time for computing. They didn't even have modern random number generators there. They were still using things like the middle square method. So if you're not familiar with this, the way we draw random numbers now is, guarantees uniformity and independence and things like that. Back then, when they were just getting used to this idea that randomness could be useful, and that came out of the World War II, the first time they were simulating with the atomic bomb. The atomic bomb kind of got everybody interested in randomness because that's how they were doing with computer methods, but they didn't really have good random number generators. So in 1953, they still were just getting interested in randomness, but they hadn't quite figured out how to harness it quite well. And Metropolis was one of the first ones to start making use of it in these sort of interesting ways. And so there, and I have this article, I think, available there, so you can look. It's in the Journal of Chemical Physics. And the article was something called Equations of State Calculations by Fast Computing Machines. So equations of state calculations by fast computing machines. So what was Metropolis trying to do? And I'm going to underline this: equations of state here. So Metropolis was interested in, so we already know about microstates. And what are the kind of macrostates? So Metropolis was sort of saying, what if we want to know what would be the volume, the pressure of it? So we have a system, it's a very high dimensional system, lots of particles in it. And we want to calculate for each temperature, for example, what would be the pressure that we would expect for this particular system if it's sitting at equilibrium, for example. And so that's what he meant by equations of states. And so we have these macro states like pressure, volume, etc. And you can think of each one of these as being a function of the microstate. And maybe I'm going to use a capital F for this. So the microstates themselves are distributed with some distribution F. And for every microstate, that microstate maps in to a particular macrostate. So for this particular configuration, we have this pressure. For this particular configuration, we have this pressure, and so on and so forth. And so the question might be, what is the average pressure that we would get out of this system? Well, that requires us in knowing the distribution of all these microstates, but I just said that we kind of know the Boltzmann distribution is kind of the important one there. And then we can say, well, given that these microstates are distributed according to the Boltzmann distribution, then how the heck do we calculate the average pressure over that distribution that we have there? So that's kind of the thing there. It's a high dimensional system in some distribution. How do we calculate this thing here? So it's a numerical problem. And the numerical problem looks a little bit like this. What is the expected value of the equation of state, capital F, over the distribution, lowercase f, where lowercase f might be like the Boltzmann distribution? And so if we were to write that out, if we think about our probability, probability courses, then it's the integral over all the microstates of capital F of state, weighted by the probability density function for that state, and again, over all the states. And this state, again, remember, these are high dimensional microstates. So I draw this as a simple integral, but really this is a multi-integral, right? I mean, so there are multiple degrees of freedom here. There's position, momentum, etc. And I have to integrate over all of those things because every particle could be in a number of different momentum and a number of different positions. And I have to say, all across all of these microstates, there's a certain probability density and there's a certain equation of state, like pressure or whatever. And I need to weight these things together and say, what is the average pressure over this whole thing? That is the problem they're trying to solve here. This is a difficult problem you can't solve it analytically. And then so numerically, how do you estimate? How do you build an estimate for that? That's what we're trying to do here. And so, so we'll end up picking up with this next time. So basically the notion here that, and I'll just finish on this note here, is that Metropolis was familiar with Monte Carlo methods. Because again, these Monte Carlo methods were sort of pioneered around 1945 or so with the advent of the atomic bomb. And so, and the reason they were called Monte Carlo methods is a code name so that during the development in the Manhattan Project, they could talk about it without anybody knowing what the heck they were talking about. Monte Carlo, casinos of Monte Carlo, that eventually got declassified. Everybody started using Monte Carlo methods. And Metropolis said, we know that there are ways to use Monte Carlo methods to solve this particular problem. So there are ways to sample, so we can approximate this expected value by randomly sampling uniformly from microstates and averaging. And so we know we can do F of the first, I'm going to just use X as my state. So this is my sample 1 weighted by density 1 plus my sample 2 weighted by density at the 2 plus all the way up to say my sample M, density M. And all that could be averaged by my M samples. And that would be a good approximation for this if I draw enough samples. And so, but in order for this to work, this M has to be very large. And so Metropolis wanted to use another innovation to try to make sampling from this microstates far, far easier and quicker. So you don't have to sample from a huge number of these microstates in high dimensional space in order to make this estimate. You can sample from far fewer ones. And if you could do that well, then you could estimate this, this function up here with far less effort. And that's what we're going to pick up next time, is how the heck we do that and how the Boltzmann distribution and all this random sampling and eventually how this annealing works. And what we're going to see is Metropolis's method will get generalized by Hastings to more general distributions other than the Boltzmann distribution. And then that will get picked up by Kirkpatrick in the 80s and 90s, and that's where we get simulated annealing. So this is our path to simulated annealing, and it starts with Markov chain Monte Carlo, which is where this is really the genesis of MCMC. So that's all I've got for you today. So you can feel free to head out if you have any questions. I'd be happy to take them. So this is, I'll say, genesis of MCMC. Oh, no, there is a Muddiest Point Sunday, and I believe the concept check 3B is due Sunday as well. That's the bottom half of the Pareto optimization. Could be wrong, but I think that's coming up. Trust Canvas's dates, but I think that's what's coming up. Yep. All right, any questions from online? If not, I will be closing the meeting. Okay. See you next week.